Hi, everybody. This is Mr. Fasoni. We're continuing Chapter 3, which is all about quadratic equations and complex numbers. And we're moving on to Chapter 3.3, which is all about completing the square. So our goals in this chapter, we have 3 of them, are to solve quadratic equations using square roots, which we've already done a little bit of. We're just going to take it a step further. Solve quadratic equations by completing the square. That's kind of our main topic. And write quadratic equations in vertex form. We're going to see that completing the square and the vertex form are intertwined. So we'll see that in a second. Remember, vertex form was something that we dealt with in chapter 2 quite a bit. All right, so concept number 1, we're solving quadratics using square roots. So we've solved quadratics in the forms of x squared equals d, where d is just some number, by taking the square root of each side, which is the inverse operation of squaring. So in other words, if I've got x squared equals 4, for instance, I can take the square root on both sides. Square root of x squared is x. And since I'm solving for x, I'm going to end up with plus or minus 2 on the right side. Similarly, I can solve for the square root of a negative number now because of what we talked about with complex numbers. Square root of x squared gives me x. Square root of negative 4 gives me plus or minus 2i. Just remember, with all complex numbers, 2i is the, or not 2i, but I is the imaginary component, that square root of the negative 1 that allows us to find the square root of negative numbers. So we can also do this with perfect square trinomials. So recall that perfect square trinomials look like this. A squared plus 2ab plus b squared. That's one of them. And the other form is a squared minus 2ab plus b squared. If I rewrite these, I get a plus b squared or a minus b squared. Oops. Let's fix that. Squares on the outside. With these perfect square trinomials, that means I can solve something. If I've got something in this format, a plus b squared equals d, whatever d is, I can go ahead and take the square root on both sides, and I'll end up with a plus b on the left is equal to whatever the square root of, plus or minus the square root of d is on the right. So if that's a little abstract, don't worry. We're going to do the problem here to kind of figure it out. So goal 1, solving quadratics using square roots. We're going to solve x squared minus 16x plus 64 equals 100 using square roots. So we're going to look at this expression on the left and go, okay, well, is this a perfect square trinomial? Well, if I look at x squared, if that's my a squared, well, I can definitely definitely take the square root on both sides and I get a equals x. So that definitely checks out. I check the very last value and assume that's my b squared. If b squared equals 64, then the square root of b squared is b, square root of 64 is 8. So that also checks out. So all I have to do is check out that middle portion. My negative 16x should be equivalent to 2 times a times b. Remember, my a value we're assuming is x, my b value we're assuming is 8. And, oh, the negative sign is, I should not have that there. I'm just looking at 16x right now. The negative sign is just part of the equation. Well, in this case, if I've got 2 times a times b, 2 times x times 8, well, that definitely works out to 16x on the right side. So I have the same value on both sides of the equation. So that definitely works out too. So what I can do is I can rewrite the entire left side of the equation as a binomial. My a value, my b value, and then remember my sign follows the sign on the equation. So x minus 8 squared equals 100. Now I'm ready to solve for x. I'm going to do an inverse operation on the left and right. Square roots eliminate the perfect square. I get x minus 8 equals plus or minus 10. I'm almost done there. Now I just have to add 8 on both sides of the equation. I'll write this in the correct order. I get x equals 8 plus or minus 10. So there's my answer. If I want to get more specific, I can solve both of these possibilities. X equals 8 plus 10, and x equals 8 minus 10. Well, x equals 18 for the first one, and x equals -2 for the second. And that gives me my two values for x in this quadratic. Now, if this is something that you're not very strong on, there are other ways to still attempt to solve this. For instance, I can try to solve this like a normal quadratic in standard form and just try to factor it. So if I've got x squared minus 16x plus 64 equals 100, I can do an inverse operation, subtract 100 on both sides of the equation. I'm left with x squared minus 16x minus 36 equals 0. Well, now I can just try to factor this using my three-step method. Step 1, do I have a GCF? No, I don't have a GCF. Got 1, -16, and -36. Doesn't work out. Step 2, do I have a special quadratic? By that I mean, do I have a difference of squares or a perfect square trinomial? Again, I don't have a perfect square trinomial, so I have nothing there. And it's definitely not a difference of squares because I've got three values instead of 2. So I go to step 3, and I just break it down into my a value, which is 1, my b value from standard form, which is -16, and my c value, which is -36. From there, I can just build my x thing, x box, whatever we want to call it. A times c is -36. My b value is -16. So I need an m and an n, where m times n equals -36, but m plus n equals -16. Well, if you think about this, if I'm multiplying two numbers to get a negative, I'm going to have one positive and one negative. So I'm going to write out some factors really quick. 1 times 36, 2 times 18, 3 times 12, 4 times 9, and 6 times 6. Well, also, if I'm adding them together and I'm ending up still with a negative number, I know that one is going to be positive, one's going to be negative because of the multiplication. And I know because my sum is negative, that the larger of the two numbers needs to be the negative. So I'm going to put a negative on all these. If I want to look at these sums, I want to find something that gives me -16. What's going to work out is an m value of 2 and an n value of -18. I could swap those. I could have an n value of 2 and an m as in Mary value of -18. Doesn't really matter either way. Now we're almost done here. Since my a value is 1, I can actually plug in these m and n values straight away and get x plus 2 times x minus 18 equals 0. And I can solve for x at that point. But also what I could do is I could build my box and do some factoring that way. I'm going to end up with the same exact answer. So my ax squared is just x squared. My c value is -36. My mx value is 2x, and my nx value is -18x. And now I just factor. This is a reverse table method for factoring. So I'm going to have x times x. This is going to be a 2 over here, and this is going to be a -18. And again, we get our factors that we had over here. And if I want to solve, x plus 2 equals 0, so x equals -2. And x minus 18 equals 0, so x equals 18. Done and done. And now we're done. We've got everything we need. So you can take either method to solve the quadratic. The square root method is nice because sometimes we're not going to end up with nice whole numbers, which makes it still possible to be solved. Whereas if we use the factoring method, it only really works nicely with numbers that are playing nice with us. All right, so we can, well, we're going to continue on to this. Concept 2a is about what we call completing the square. So we can use the idea of a perfect square trinomial to modify a quadratic to make it factorable. We call this completing the square. So let's look at the diagram here. Remember that multiplication is effectively just finding the area. You multiply 3 times 5, you get 15. Think of a 3-foot by 5-foot room would be 15 square feet. Well, what this diagram has here is it's got the first 2 parts of a quadratic. It's got my ax squared, and it's got my bx, all in this rectangle here on the left. Effectively, what we've got here in the diagram, actually, I'll just stay over here. I've got x times x equals x squared, and then x times b equals bx. Well, it's a long rectangle, but what I can do is I can take this bx here, I can split it down the middle. So each side is half of bx, or rather, b times x divided by 2. I cut it in half. If I move that half down here, what I do is I've created 3 parts out of 4 for a square. I've got the same length on each side, x plus b over 2, because half of b, remember this is half of b here, and x plus b over 2 down here. If I multiplied these together, I'd have x squared, x times b over 2 is b over 2 times x, b over 2 times x is b over 2 times x, and then these 2 b over 2's would multiply to give me that last corner. So I can take b over 2 times b over 2, which would give me b squared over 4. And that would complete what we call the square. It's kind of a weird concept, but what we can do here is we can take an existing trinomial. I've got x squared plus 14x plus c. We're looking for the value of c that makes this a perfect square trinomial. And then we're going to rewrite the expression as the square of a binomial. So again, think about this as that area model. I've got x squared and 14x here. Well, I know it's going to be x times x, and this is going to be 14. This is a length, so this is like saying x plus 14 here. So if I want to do this area model thing, I can cut 14 right in half. That's going to be 7. So this distance here is going to be 7, and so is this distance here. And what I can do is re-diagram this. I still have my x times x box in the upper left corner for x squared. But now I've got a new box. It's half the length of the original right side box, and I've moved it. So I've got 7 here and 7 there. So I get 7x and 7x. Well, now I've got almost my entire square made. I just need to figure out what this little last box is going to have to be. So if you look at this model, we've got 7 times 7. So 7 times 7 is going to be 49. So what I've effectively done then is added some extra values to the original diagram. I rearranged the original diagram to make this kind of, I don't know what this shape is, this shape here. And to finish out the square, I just needed that lower right-hand corner. So I've effectively got, right now, x plus 7 times x plus 7. To fill in that last bit, I just had to add the 49 to make the complete square. That's what we mean by completing the square. So x plus 7 times x plus 7 is going to equal x squared plus 7x and 7x is 14x plus 49. And I've managed to create a perfect square trinomial. So going back here, the value of c would be 49, and my expression as a square of a binomial would just be x plus 7 squared. That's it. So I've built a perfect square trinomial by finding my c value, and then I converted it back to a binomial. So let's go ahead and continue. So we can use this idea of completing the square to solve quadratics. Now, if we complete the square to solve an equation, we have to add the same amount to both sides of the equation. So be mindful. If I'm adding like 49, I added 49 to this equation. I have to add 49 to the other side of the equation if I'm trying to solve for something. So let's go ahead and do some examples to see what we mean. And I'll fill in a little bit more information as well as we're going. So I'm solving a quadratic in the form ax squared plus bx plus c equals 0 when the a value is equal to 1. So I want to solve this by completing the square. Okay, well, so my strategy for this, I kind of did it fast above. If I've got an equation like this, x squared minus 10x plus 7 equals 0. If I want to complete the square, this is not a perfect square trinomial right now. This 7 is messing it up. I need a different number than 7. So what I'm going to do is I'm going to move my c value, my current c value. Let me write these down for us. Our a value currently is 1. Our b value is negative 10. And our c value is positive 7. Well, the a and b value are going to stay the same, but that c value is going to change. This is my current c value, but I'm going to create a new quadratic that has a c value that makes it a perfect square trinomial. So I'm going to move the 7 from the left side to the right side. Now I've got x squared minus 10x equals negative 7. So what I want to do now is fill in some blank here to make this left side into a perfect square trinomial. Well, to do that, I'm going to note my b value. My b value is negative 10. And again, this is like the diagram, right? X times x is x squared. That's my first part of my equation. And then I've got a negative 10 times x, which gives me negative 10x. That's my second part of the equation. So my first step is to find my b value, which I did. Second step is to split it in 2, divide it in 2. Well, b divided by 2 is just going to be 5. I'm sorry, negative 5. So what I'm doing is I'm splitting that b value up to create that second diagram. Still have x squared here, but I'm going to have a value of negative 5 and negative 5. I've moved half the square down, which gives me the following setup. Well, I'm going to use this b over 2 value, negative 5. I know if I take negative 5 and multiply it by negative 5, it's going to give me, let me change my colors again, negative 5 times negative 5 is going to give me that little last square in the corner. Well, negative 5 times negative 5 gives me positive 25. And that would complete my square. So b over 2 squared, that's what I did there, negative 5 times negative 5, in this case gives me positive 25. I'm going to take this value And I'm going to place it up here. So what I get is x squared minus 10x plus 25. I've completed the square on the left. Remember, I added 25 on the left side, so I have to add it to the right side. Negative 7 plus 25 gives me positive 18. Well, now we're getting somewhere. Now we've got a perfect square trinomial. And I already know what it factors down to because I've completed the square here. It's going to be 2 factors of x minus 5. So I can rewrite this immediately as just x minus 5 squared on my left side equals 18. So now we're getting somewhere. We know it's going to be equal to 18. Well, to solve this, now I'm just doing inverse operations. Take the square root on each side. I get x minus 5 on the left equals plus or minus the square root of 18 on the right. So I'm almost done. Let's add 5 to both sides. 5's on the left cancel. I end up with x equals 5 plus or minus the square root of 18. We're basically done, but one last thing we can do to clean it up is we can convert the square root of 18 into a cleaner, simpler root. Well, the square root of 18 is the same as the square root of 2 times the square root of 9. The square root of 9 is just going to be 3, so I can rewrite this as 3 times the square root of 2. So my final form, as it were, is x equals 5 plus or minus 3 times the square root of 2. There's the solution to my quadratic. If I plug that value back in for x on the original equation, did all my multiplication, I would end up with that exact value. Or I would end up with an equation that works, rather. So in other words, if I plugged in 5 plus the square root of 18 for x, and then plugged it in there as well, did all the calculations, added 7, I would get 0. If I did 5 minus the square root of 18, I'd also get 0 when I calculated it all out. So that's solving quadratics when our a value is equal to 1. We can complete the square and we can solve. And as you can see, completing the square is a little bit more powerful because we can deal with these square roots. Factoring does not really work that well for that unless you've got a really good mental calculator for figuring out what those factors are going to be, which I don't recommend. It's just a lot of work and it's a lot of guess and check. All right, so let's try goal B part 2. Solving the same type of equation, but when a is not equal to 1. This just has an extra step. It's nothing special. So I'm solving 3x squared plus 12x plus 15 equals 0 by completing the square. Okay. Not a huge problem here. All we have to do is divide by 3 on both sides. If I divide by 3 on the left, well, I'm left with x squared plus 4x plus 5 equals 0. Now at that point, things become a lot easier to deal with. We can address this problem in the same exact way. X squared plus 4x plus 5 equals 0. So I'm going to do an inverse operation. I'm going to move my 5 from the left to the right. And I'm left with x squared plus 4x equals negative 5. Well, I can finish this out quickly. I want to complete the square. Again, if I wanted to visualize it, I've currently got this. So my goal is to find my b value. My b value is 4. I'm going to divide b into 2. I'm going to have b divided by 2 equals 2. So I redraw this schematic for this diagram. Still have x squared, but now I've divided the right side block into 2 pieces, each with a length of 2 on one edge and x on the other. And now the only thing I need to figure out is that little space down at the bottom here. Well, it's just going to be 2 times 2, which gives me 4. So b divided by 2 squared is going to be 4. So 4 is what I'm going to be adding to my equation to make a perfect square trinomial. So if I add 4 on both sides, I get x squared plus 4x plus 4 equals -1. We're almost done here. Again, I know what my factors are of my perfect square trinomial. I can rewrite this trinomial as x plus 2 squared equals -1. Now it just comes down to taking the square root on both sides. Square root of x plus 2 squared is going to just be x plus 2. Square root of -1 is just going to be I, or really plus or minus I. Well, I solved this by subtracting 2 on both sides of the equation. I'm left with x equals -2 plus or minus I. So more specifically, I've got x equals -2 plus I and x equals -2 minus I. Those are my solutions, and I'm done. All right. So that's solving a quadratic by completing the square. And we can do this with really any quadratic we're given. Some of them might end up with some crazy fractions when you're dividing, but you can still solve them. It just gets a little bit messier. All right, we're almost done here. In fact, I think these are the last 3. And actually, I think that's an extra slide from previous class session. So we've got 2 slides to go. So concept 3 is writing quadratics in vertex form. So remember in chapter 2, we were able to convert quadratics from vertex and intercept forms into standard form by following the order of operations, or PEMDAS, or BODMAS, or whatever we want to call it, GEMS. So we can convert to standard form. That's easy. Then in this chapter, chapter 3, we found that we can convert from standard form to intercept form by factoring. It takes it back to that more intercept form look. And then finally, in this section, we're going to convert from standard form to vertex form using the completing the square method. So let's go ahead and try this. So I've got an equation here, y equals x squared minus 12x plus 18. And we want to rewrite this in vertex form and then identify the vertex. Well, we know once we're in vertex form, it's really easy to get the vertex because it's already in there. So I'm going to try to use my color coding that I've used throughout the sections. Standard form looks like the following. Ax squared plus bx plus c, and I used red for A, blue for B, and green for C. That's standard form, and our goal here is to convert it into something that looks like vertex form. Remember, vertex form is the following. A times x minus h squared plus k. If you recall, h comma k is my vertex. Okay. So if I want to convert this to vertex form, it's really quite straightforward. I'm just going to use the completing the square method. I'll do this on the left here. Start with red. So if I got the equation y equals x squared minus 12x plus 18. and I want to convert it to vertex form, well, I need to complete the square to start that. So I'm going to subtract 18 from both sides. Just going to set that 18 over to the side for right now. I end up with y minus 18 equals x squared minus 12x. So now I've got a situation where I can complete the square. Remember, my diagram would look like this. X times x is x squared, and then the extra part to the right is negative 12x. So 3 steps. Find my b value. Well, my b value is negative 12. B divided by 2, well, that's going to be negative 6. So I can then redo this by cutting it in half. So after step 2, my diagram now looks like this. These are my halves of the original right side rectangle. And then finally, I need to figure out what my b divided by 2 squared is. That's just going to be negative 6 squared or positive 36. So this little spot here that completes the square for me is just going to be negative 6 times negative 6, which equals 36. Well, now I'm ready to go. All I have to do is add 36 to both sides of the equation. I get y plus 18 equals x squared minus 12x plus 36. Now I've got a perfect square trinomial. I already know what the factored form is going to look like, because I've got it right there. So I can rewrite this right side as x minus 6 squared. And then to get it back into vertex form, I just got to get y by itself. So I'm going to move, I should change my color again. I'm going to move this positive 18 back from the left to the right. I end up with y equals x minus 6 squared minus 18. Well, what do you know? Isn't that vertex form? My a value in this case is just a 1. My h value, well, if I've got a negative 6 here, that means my h value is 6. And then my k value is negative 18. Well, because I've got my h and k value, I know what my vertex is. Vertex is just h comma k. So in this case, my h value is 6 and my k value is negative 18. At that point, I'm done. I've converted it to vertex form here in the blue. And then once I have my vertex form, I have the actual coordinates of my vertex. And at that point, I'm done. I've gotten everything I need. And this is from the previous section. Apparently, I didn't get rid of it, so ignore it. And that's our last goal, and we're done. We found the vertex, we rewrote it in vertex form, and we're good to go. Just as a little aside, I'm going to go to Desmos really quick, and I'm going to plug that equation in just to show what it looks like. Y equals x squared minus 12x plus 18. And if I go way down here, sure enough, at 6 comma negative 18, there is my vertex, just where I thought it would be. I can even show that these are equivalent equations. Y equals x minus 6 squared minus 18. As you can see, the two graphs are right on top of each other. Blue, red, same graph. So there we go. So I hope this was informative. This homework will be due 2 days after the 3.2 homework. I'm going to go ahead and put this online immediately so you guys have it. The assignment will probably come out tomorrow morning because it is quite late, 11 o'clock here now. If you have any questions, please hit me up on Teams or email or Remind, and we'll see you very soon. Thanks.